Hello class, this is CSE-4600, Section 1, Week 6, Spring 2025. Okay, so let's talk about what we're going to be doing for our Project 1. So we are going to be writing a CPU scheduling simulator. It's really a calculator, but I called it a simulator just because. Okay, so it is a project in 6 parts. Part 0, Part 1, 2, 3, 4, and 5. So Part 0 is a practice problem. So we could just try out CPU scheduling algorithms using some practice problems, but I think it'd be more fulfilling if instead of doing some practice problems by hand, we would write an entire program that would calculate turnaround and waiting times for us. So part 0 is going to be a practice problem. I pulled this from the book. So you are to calculate the average waiting and turnaround times for a set of 5 processes using 4 different scheduling algorithms. First come, first served, shortest job first, round robin with a quantum of 2, and round robin with a quantum of 4. You can use the table below to get started, so you can, and I would also recommend that you would draw a Gantt chart so you can visualize how long each process runs for. If you know how to use Excel, I would also recommend that you also use Excel. So we can use Excel to draw a Gantt chart for us that would help us visualize we use a Gantt chart to help visualize how long processes run for. So this example here is for first come, first serve. We run processes in the order in which they lined up in the queue. So process 1 had a burst time of 10 milliseconds, followed by 6, 2, 4, and 8. So if we just eyeball this and see 10, 6, 2, 4, and 8, we have our 5 processes here. This is first come, first served. And then, for example, we can eyeball this and we know all our processes arrived at the same time, at time 0. Process 1 was the first in line, so it waited for no time at all to start running, and it then finished at time 10. Therefore, we know from here that process 1 had a wait time of 0, and then followed by that, a turnaround time of 10. So, yeah. Also, you can also use Excel to quickly calculate the average waiting and turnaround time. So you type into a cell equals average, and then let me just reset it so I can show you how it works. So you type in equals average, left parenthesis, and then you highlight these 5 cells, press enter, and it will calculate the average of these 5 cells here. Well, there's nothing in here right now, so it's averaging only one thing, and that average was 0. And then you would highlight this cell and drag the sizing handle so you can then use the same calculation for all other columns here. So this way we can quickly figure out the waiting and turnaround time. If you have Excel, then this will make your homework a lot easier. Should you use Excel? Well, if you have it, why not? It's just a matter of, do you know how to use Excel? So, if you want to use Excel, go ahead. If you do use Excel, I would recommend that you post the workbook, the Excel spreadsheet, as part of your submission for Project 1. So you can either fill out this table here, or you can just copy the table and put the Gantt charts on the side, and then use this table to calculate your average waiting and turnaround time that way. Excel is basically a calculator with XY coordinates, if you think about it. Anyway, also, unrelated topic, but Excel is Turing complete, and I know this because someone tried to make an entire CPU using Microsoft Excel. Meanwhile, someone else tried to use Microsoft Excel as a game engine. So, yeah, so unrelated banter, let's get back to work here. Okay, so that is part 0. Try out the problem here and see how long each process needs to wait for. And then you calculate the averages. Okay, so parts 1, 2, 3, and 4 are all parts where you do coding. Part 5 is experimenting once your calculator has been written and running. So there are 3 things you're going to experiment in part 5. Those are: confirm the results that you got in part 0, run round robin with an increasing size for the quantum. So we're going to run it with a quantum of 2, 4, 6, 8, 10, and 12, and see what happens as we get the quantum larger and larger. And finally, we're gonna run our program once again, but with a different set of processes. So generate a different sequence of 6 processes with random run times, and then find the waiting and turnaround times for those 6 processes. Once again, you can just use Excel to help out with finding the average waiting and turnaround time for that. But once we have the calculator running, we'll basically get all our data points for free, basically. So the rest of the video here is instructions on what, it's more like guidance on what you are to write. If you look in the instructions for parts 1, 2, 3, and 4, you are provided code skeletons, as I like to call it, on what you need to write. So you do have some preliminary code that is there to get you started. However, much of the work is filling in the blanks here. So ask the user for user input, allocate memory, enter burst times, and then call each scheduling algorithm. This right here is commented out code. As you proceed, you are going to comment out one of these scheduling algorithms to see how well it works. If you feel like you can figure out what's needed for each of these steps here, then have at it. If you do need guidance, however, then the rest of the video will be that guidance. Okay? So we're gonna start with part 1, starting now. I think my webcam just broke. Okay, we're gonna go at the webcam for that. Bye bye, webcam. Okay, so we're gonna begin with part 1, where we write our boilerplate code. So I already have my VirtualBox running here. All I need to do right now is I'm gonna open my text editor up, and I'm simply gonna type in our boilerplate code here. So include standard io.h, include standard library.h, and finally standard include standard bool.h. I'm then going to save this document as a .c file. So I have it so that it's gonna be saving into my project 1 folder here. I'll call it project1.c. Press enter, and there we go. Now I'm gonna continue on with our 3 function prototypes. So, hold on, let's see if I can get the webcam back. Okay, looks like I got that webcam back. Okay, so we're gonna now write our function prototypes. So we're gonna begin with our first function prototype. So these are all functions that are just gonna return nothing. So they have return type void. They're just gonna print out results to the string. So void fcfs. So all 3 scheduling algorithms take in 2 parameters. The first one is the burst times, and this is an array. This is an integer pointer to an array, because we don't know how many processes we're going to be running our program with, so we must dynamically allocate the right amount of memory for our task here. So the data type for the first argument is int star, and we're going to call it burst times. There we go. The second argument is the number of processes. There we go. And that's for first come, first served. For shortest job first, it's the same thing, but except I call it SJF. I'm just gonna add a space so that way everything lines up perfectly. That's just me though. So, the third one is round robin, so I'll just copy this line again, replace SJF with RR, short for round robin, but we need a third thing to pass in, and that is the quantum. The behavior of round robin depends on how large or small the quantum is. So I'm just gonna add in a third parameter, int quantum. There we go. Now we can get to work with our main function. So int main here and there. So now we can get to work on our main function. So let's declare a few variables here. So this is gonna be some, we're gonna say int star burst times and int num processes. There we go. Okay. Our next step is to allocate memory for an array that is gonna be for our burst times. So burst times plural. Okay, there we go. Okay, so we're gonna ask the user, that's you, for the number of processes that we're gonna run, and then the program is going to allocate memory for those burst times. So I'm simply gonna say printf how many processes are you running, and I'm not gonna add a \n because I want it so that the input will be on the same line as our prompt line here. So how many processes are you running, and then the user types 5 on the side. There we go. So I'm gonna type in scanf. I'm gonna type it as the same thing you would if you're to format output using printf. So it's gonna be %d. It's %d specifically so that we can type in input as a base 10 number. So I'll say %d, and we need to store this in our variable. So for that to work, we need to pass in the address of our num processes variable. So num processes, there we go. And then I'm just gonna add an extra printf line just as a spacer. Actually, no, I'm not gonna do that just yet. Okay, so we have the program asking the user, how many processes are you running? And then with that information, we can allocate memory for our burst times. So the function for that is malloc, and then we pass in number of processes times however large an int is. So size of int. That's not right, because this actually needs to be on the right hand side of an assignment operation. So on the left hand side, we need burst times. And then we say malloc num process size of int. But we need to cast this as a pointer to an integer. So int star, and then we have our memory allocated. Okay, so there we go. We ask the user to provide the number of processes we're running, and the program allocates enough memory for those processes. Because we are allocating memory here, at the end of the program, we need to call free and then pass in that pointer, so that way we deallocate memory correctly and we don't end up with a memory leak. So let's do that really quick. I'll say free burst times and say return 0. So that is the end of the program. Let's continue on with the middle of the program. So now I'm going to ask the user, how long are we running each process? So we're gonna do that using scanf, but in a for loop. So, enter the burst times for each process. So, for int I equals 0, I is less than processes I plus plus. Now, I'm gonna cheat here and just copy these two lines again. So we're gonna ask the user, enter the burst time for process %i of %i. Since now I have these, I like to think of these as blanks. So now that we have these blanks, we need to pass in two more things to printf. That's going to be I and num processes. So we're going to say enter the burst time for process 0 of 3. Enter the burst time for process 1 of 3. Enter the burst time for process 2 of 3. There's no process 3 of 3 because we've got it starting at 0. And then we pass into scanf the address in which we are to store our input. It's not going to be num processes, rather it's going to be ampersand burst times I. Oh, by the way, I am missing a comma here, so let me add that here real quick. There we go. We can stop our coding here and simply run our program just to make sure everything is running properly. So I'm going to use the terminal here and say gcc-o project1 project1.c, press enter. Okay, it compiled. // project1. How many processes are you running? Let's run 3 processes. Let's do a runtime of 3, 1, and 4. And nothing happened because we programmed nothing else to happen at that point. But we allocated memory and it deallocated that memory. Okay? So it works. Okay, so optionally you can just print out we can print out what our program's processes burst times are. So this is optional, so print out what was typed just for fun. So for int I equals 0, I is less than num processes I plus plus. And then we're simply going to say printf and %i burst times I. There we go. Okay, so actually no, that isn't quite right. Rather, I need to add a space like that. However, that will offset that means the first line will have an extra space, and I don't want that. But rather, this is actually an advantage because I'm going to add another printf right before that. So printf there we go. The following processes will arrive at time 0. And then we're going to have a space, and then the burst time of the first process, then a space, then the burst time of the next process after that. And then, just for completeness, I'm going to say printf \n. There we go. Let's recompile this to see how well it runs. So, clear project 1. Let's do 5 processes, and for fun, we're going to do 3, 1, 4, 1, 5. I don't think I compiled it yet, so let me try that again. So let's recompile the program. Project 1. We're going to do 5 processes, so 3, 1, 4, 1, 5. And the following processes will arrive at time 0. 3, 1, 4, 1, 5. So I guess for completeness, I'm just going to say The following processes will arrive at time 0 with the following burst times. There we go. The following processes will arrive at time 0 with these burst times. So let's recompile the thing. Project 1, 5 processes, 3, 1, 4, 1, 5. There we go. So now we have our main function almost done. What I'm going to add is a function called to FCFS, and I'm going to pass in burst times and num processes. Then I'm going to pass in those two arguments into SJF. And finally, round robin, burst times num processes. There we go. However, we don't have the functions declared just yet. I have the prototypes, but we don't have the declarations yet. So I'm just gonna comment them out for now. Give me a minute. And oh yeah, remember that round robin requires a third argument, and that's the quantum. Let's use a quantum of 3 for now. We're gonna change that later on. So now we have these commented lines. We have these 3 lines commented out. We're gonna uncomment them one by one as we write each scheduling algorithm. So the first one we're gonna write is first come first serve. There we go. So here is our skeleton code, and this is the simplest one of all. And that's because first come first serve is pretty simple after all. So we run our processes in the order in which they fell in line. So we're going to write our function for FCFS. So I'm going to say void FCFS int star burst times int num processes. At the end of the function, I'm going to say return. There we go. Let's begin with our variables that are declared at the top. So I'm going to say int time elapsed equals 0, float average waiting time equals 0.0f, and float average turnaround time equals 0.0f. Now, the instructions have us use a for loop, and the thing about first come first serve is in the case where every process arrived at the same time, that's all we need. So I'm going to write a for loop, calculate each process's we're gonna use a for loop to calculate each process's waiting and turnaround time. So for int I equals 0, I is less than num processes I plus plus. We want to calculate the waiting and turnaround time. However, we also need to count up the time elapsed, because the turnaround time, we're going to count up time as we go, so we need to keep track of that using our time elapsed variable here as a counter. So time elapsed plus equals how long is our process running for? So actually, before I do that, I'm going to say int burst time equals burst times I. I like to write my code like this for ease of understandability. So I'm going to say int burst time equals burst times I, and then I'm going to say elapsed time equals, no, not equals, plus equals, because we're incrementing our elapsed time by our burst time. Elapsed time plus equals burst time. There we go. from here, we can calculate the waiting and turnaround time. So I'm going to say int waiting time equals. So what is the waiting time? Well, it's how long the process was waiting in line, but we have already incremented our elapsed time. So maybe we should start first with our turnaround time, because that's easier to calculate. Turnaround time is the amount of time from when a process first fell in line in the queue for the CPU to when the process finished its work. So the time from when a process was submitted to the time to when a process finished its work. Since all our processes arrived at the same time, and we have this elapsed time value here, keeping track of how much time has passed since the start of the simulation, turnaround time is basically elapsed time. So I'm going to say int turnaround time equals elapsed time. So what's the waiting time? Well, it's the portion of the turnaround time the process has spent not running. So if a process ran for some amount of time specified by our burst time, we can subtract that from our turnaround time and get our waiting time. So it's going to be turnaround time versus waiting time. No, our waiting time, I misspoke. Our waiting time is turnaround time minus our burst time. So turnaround time is waiting time plus burst time. Put it another way, waiting time is turnaround time minus burst time. So I'll say it as that. Turnaround time minus burst time. There you go. We got our waiting time and turnaround time now. So all I gotta do is print out this result in a printf line. So okay, so I'm going to simply say printf process percent I colon backslash t, and that places a tab in our output so that everything lines up in columns. I'm going to say that, and then I'm going to say bt, short for burst time. I'll say bt, short for burst time, colon, space, percent I, backslash t, to add another tab, TAT, short for turnaround time, colon, space, percent I, backslash t, WT, colon, space, percent I, backslash n. So now we need to print out the process ID, the burst time, turnaround time, and waiting time. So let's do that really quick. So the burst time is, okay, so the first thing we need is the process ID. Since processes arrived in the order that they fell in line in, we can just use I for the process ID. Next, we can put in our burst time, our turnaround time, and waiting time. And there we go. The last thing we need to do is add these waiting and turnaround times to these two variables here. That way we can then calculate averages first. After that, I mean. So that is average waiting time plus equals waiting time and average turnaround time plus equals turnaround time. There we go. So after all that, we can print out our averages. So that is going to be average waiting time slash equals, so we're going to divide our waiting time by the number of processes we have. We probably don't need to do this because it's already a float, but I'm going to do it anyway, just to make sure we don't accidentally perform integer division somehow. So, float, num, processes, and average turnaround time slash equals float, num, processes. So, we find the average by, of course, adding all of our numbers together and then dividing by the number of numbers that we have. So now I'll just do it in another printf line. So printf average WT. Well, I have a turnaround time and then waiting time in here, so I'll just follow that order here as well. So average TAT colon, give me a minute, average TAT colon space percent D. I'm going to do that because I want to make sure that this is printed out as a decimal value with decimal points after that. So AVG TAT percent colon space percent D backslash T, so I have a tab after that, and then I'll say AVG WT colon space percent D backslash N, because we don't have any more output after that. So I'm going to say that, comma, average turnaround time, average waiting time. There we go. So let's see how well this program works. So I'm going to type in clear, I'm going to recompile my program, and now we got some errors. So looks like there were some mismatches after all. So elapsed time undeclared? Oh, I said time elapsed, but then I said elapsed time. Let me fix that. Elapsed time, elapsed time. Okay, so that should take care of one error. So if I recompile it, I still have the error with the time elapsed versus time elapsed time. I guess I didn't save it yet, so clear, recompile. So now we have that formatting error where I have to change a few things from %D to %F. So they're all on line 72. So yeah, it turns out it wasn't %D, it was %F. So let me fix that really quick. So hopefully that should fix up the error. Clear. There we go. So now I can do ./project1. How many processes are you running? So let's do 5. And I'll do the same sequence of processes as before. 3, 1, 4, 1, 5. And oh yeah, I think I forgot to uncomment out the function call. So we need to uncomment out that one function call, so that way the project will run using first come first served. So project 1, 3, 1, 4, 1, 5. Oh, oops. I guess I jumped the gun here. So let's try it again. So project 1, we are running 5 processes. 3, 1, 4, 1, 5. So if we read this, we have process 0 with a burst time of 3, turnaround time 3, waiting time 0. Process 1, turnaround time 4, waiting time 3. Process 2, turnaround time 8, wait time 4. Process 3, waiting time 9, turnaround time 9, wait time 8. Process 4, turnaround time 14, wait time 9, and then we got the averages down here. 7.6 for the average turnaround time, 4.8 for the average wait time. I'm going to make one change right now, and that's because I have it so that it's waiting time and then turnaround time in the table. So I'm just going to swap the order of waiting time and turnaround time so it's consistent with our table that we have in the instructions. So give me a minute. I'm also going to fix up that backslash, and that's supposed to be a backslash T. Okay, I got the fixes all done, so clear, recompile the project. There we go. Okay, there is one more problem in here. I think unknown escape sequence, I think I put in an incorrect character somewhere. Okay, so those were supposed to be backslash T. Those were supposed to be tabs. I think I accidentally erased the tabs. So let's try that again. Clear, recompile. Missing the wrong variable name. So there we go. Let's try it again. So we're gonna run our project with 5 processes with burst times 3, 1, 4, 1, 5, and now it's formatted properly. So process 0 has a burst time of 3, wait time of 0, turnaround time of 3. Process 1 has a burst time of 1, wait time of 3, turnaround time 4. And that's because I had to wait for process 0 to finish. Process 2 had a burst time of 4, wait time of 4, turnaround time of 8. And that's because I had to wait for the previous 2 processes to finish, and so on and so forth. And we got our average waiting time and average turnaround time. So we got it. We got shortest. So we got first come first served done. We got one scheduling algorithm done. Let's do the next one, and that one is shortest job first. So the code for that is a bit more involved, and that's because there are a few things we have to add here. So I'll walk you through with that. So SJF void SJF int star burst times int processes return, and we're gonna declare pointers and variables. So we need a few pointers here. So that is int star. The first one is our sorted burst times. So we're gonna copy all our burst times into another array and then sort that copy. That way we don't mess up with the originals at all. We also need a second array that contains the process IDs, so that way we know which process was which, because we are sorting all the processes by burst time. We want to know which process was which. So int star sorted burst times equals int star malloc num processes times size of int. There we go. Now I'm gonna duplicate this line, and instead of sorted burst times, these are process IDs. There we go. Same thing as before. We're allocating another array's worth of space, but for our process IDs. Now we need int time elapsed equals 0, and then much like with FCFS, we need average waiting time and average turnaround time. I'm just gonna cheat and copy paste those variables. So now we have variables for sorted burst times, process IDs, time elapsed, waiting time, and turnaround time. We are gonna copy our burst times into our sorted burst times array because we don't want to touch the original burst times. So we're gonna do this in a for loop. So for int I equals 0, I is less than num processes I plus plus. copy burst times into a new array to be sorted, and write down the process ID. So we're actually going to do two things here. First is we're going to say sorted burst times I equals burst times I, and then process IDs I equals I, because the process IDs are assumed to be ascending. The process IDs are assumed to be the index number of where that process was in our burst times array, where it was in that array. So we have now copied our burst times into a new array, but also we now have an array that contains all of our process IDs. Now we need to sort our sorted burst times. So there are several ways we can do this, but let's go with a selection sort. So selection sort is one of those big O of n squared sorting algorithms. For our purposes, since we have such small arrays that we're working with, we can get away with selection sort here. So selection sort requires us to use a doubly nested for loop, but I'll just copy it down right here. So okay, so for us to work with selection sort, we need a doubly nested for loop, but we also need a few more variables before we even begin. So okay, so we're gonna say int smallest burst time. And hold on. Okay, my bad. Turns out we probably don't need this smallest burst time right here. So for now, we could probably just get rid of, not use this variable here. So we don't need this after all. My bad. So we just need we need to keep track of the index of the smallest number that we found. So I'm just going to say index of smallest, and we'll set that to be -1. Now, we need a doubly nested for loop for this. So for int I equals 0, I is less than num processes -1 I plus plus. So the nature of selection sort is we're gonna start at the first element, and then we're gonna compare all successive elements with that first element and find what's the smallest element we found, and then we do a swap. Then we go to the next element, compare it with all successive elements after that, find the smallest element there, do a swap. Go to the next element, compare it with all successive elements after that, and do a swap again. And that's why we need to start at 0 and end right before the last element, because if we do it at the last element, there's nothing else to compare. And we need to be comparing the current element with all successive elements after that. So that's why we need I equals 0, I is less than num processes -1, I plus plus. We also need, as I said, we also need a variable to keep track of what is the index of the smallest value we've found. So, in this for loop, we need another index, and that is int index found. And, oh, my bad. We actually don't need this index of smallest right outside either. So it turns out that was an extra variable that I had erroneously copied. because I thought I needed another one outside. But no, we need just the one on the inside. So index found equals, so index found equals I. We're gonna compare the first element with all successive elements after it to see whether there's a smaller element than that. If we do, we're gonna perform a swap between the real smallest element. So index found here really should be index of smallest. So I'll just copy the name of that there. So let's keep going. To do a comparison with every successive element after the current one, we need another for loop. So for int j equals 0, j is less than num processes j plus plus. So this is our doubly nested for loop. If we find a even smaller element, we're gonna update the index of the smallest element. So if sorted burst times j is less than sorted burst times index of smallest, we're gonna update our index of smallest and say index of smallest equals j. So this is the basic idea behind selection sort. And after we perform this outer for loop, we are going to perform a swap. So we're gonna swap our burst times. So we're gonna say int, we need a temporary variable. So we're gonna say int temp equals sorted burst times I. I'm gonna say sorted burst times I equals sorted burst times index of smallest. And then I'm gonna say sorted burst times index of smallest equals 10. So that's how we swap two variables in C code. There is a swap function in C++, but we don't have it here. We could just write a helper function and call that if we need to, but we can write it like this and it will still work. So once we find the index of the smallest value in our array, we perform a swap. But we also need to swap the process IDs as well. So when we swap the burst times from between process, when we swap the burst times at positions I and j in the array of sorted burst times, we need to perform the same swap at positions I and j for our process IDs. So we need to do two swaps here. So I'm just gonna copy that, paste it here, and we're gonna say swap PIDs. We already declared a variable called temp, so I'll just delete that int, so it's temp equals not sorted burst times. We're gonna be swapping values in our process IDs. So values in our process ID array. So I'll replace each instance of process. I'll swap out each instance of sorted burst times with process IDs. So now we are doing two swaps. We're swapping burst times so that they are sorted, and we're gonna swap process IDs in that other array so that we know which process was which. So now we need to perform our shortest job first calculation, and that is basically the same as this for loop up here. So really what we could do is copy our code from first come first served and paste it down here so we can calculate each process's waiting and turnaround time. And that's almost it. Shortest job first, at a conceptual level, the calculation for it is basically sort the processes by burst time and then perform first come first serve on it. However, we need to do one more thing. process %i, that is incorrect. What we instead need is to pull the process ID from our array of process IDs. So I'm just going to copy this, and instead of I here, its process ID is I. And because all the variable names are the same as before, oh, one more thing. Burst times, that is not the right one. We need the one from the sorted burst times. There we go. So we have our sorted burst time. We increment our elapsed time. And then we calculate our waiting time and then our turnaround time. And then we print out the burst time, waiting time, turnaround time for our process. And then we calculate our average. So the only addition to SJF is the fact that we have to sort our burst times. So let's see how well this works now. Clear. I'm gonna recompile the project, and then I'm gonna say project 1. Oh no! I forgot. I forgot to uncomment out this line. So let's do that really quick. Clear. We're gonna recompile our project. I'm gonna say ./project 1. I'm gonna say 5 processes, and I'm gonna say 3. No, 1, 3. I screwed it up. So let's do it again. 5 processes with burst times 3, 1, 4, 1, 5. And look at that. Okay, so now we have, yeah, look at that. We have processes not quite in the right order though. So really this should be 1, 1, 3, 4, 5, but it's 3, 4, 1, 1, 5. So our sorting algorithm isn't quite working yet. So it's just calculating the average and average times for the wrong order of processes. So I'm gonna debug this and see what went wrong. Okay, you want to know what the bug was? For int j equals 0 is incorrect. It should be for int j equals I plus 1. So we were overscanning the array. So for each value in the array, we have to compare it with every successive element after that. What we were doing previously, we were scanning the whole array. Oops. Clear? Let's try that again and see if we get the right result this time. We're gonna do 5 processes with burst times 3, 1, 4, 1, 5, and hopefully it should be 1, 1, 3, 4, 5. And it is! 1, 1, 3, 4, 5. So I guess the weird thing is we have 2 instances of processes with burst times of 1. So we have process 1 and then process 3 with burst time 1. Okay, so we got 1, 3. The next process after that is process 0 with a burst time of 3, and then process 2 has a burst time of 4, and then the last process has a burst time of 5. So the order of processes should be 1, 3, 0, 4, 2, and then the burst time should be 1, 1, 3, 4, 5. And now we have the average wait time and average turnaround time for that. Alright. You know, glad I noticed it. It would probably help to say which scheduling algorithm we're using. So, for FCFS, I'm going to add an extra output line here. I'm just going to add another line here saying print f the times for FCFS are as follows. So this is for FCFS, and then I'm going to add a similar line for SJF. So not there, but rather here. So SJF. So I'm going to recompile this once more. Okay, so there we go. So the times for FCFS are as follows, and then the times for SJF are as follows. So there we go. Now we have extra lines of. Now we have extra input output lines, so you know which algorithm is which. Okay, so with that, our last scheduling algorithm is going to be for round robin. So I'll clear all that, and let's get to work with round robin. So this one's a bit more involved. So there we go. So round robin has 3 parameters, and the third one is the quantum. Int quantum. There we go. And let's start writing out that code. So the code for round robin is as follows. So we need oh wait. You know what I forgot? For shortest job first, we had memory being allocated, and we need to free that up. So I need to add this free. Free sorted burst times, and then free process IDs. Yeah, because without those 2 lines, we're gonna end up with a memory leak. So I guess I ended up with a memory leak just now, but that can only be resolved if I restart the virtual machine. Right now I'm just gonna ignore it, and hopefully nothing too bad happens. It's under the justification that this is a small memory leak, and yeah, I'll just deal with the consequences of what I just did should it come up. But yeah, anytime we allocate memory like this, we need to free it up when we're done. So free sorted burst times, free process IDs. So those were the missing steps that we had to do. Okay, with that, let's get back on track with round robin. And that is, we're gonna declare our variables and pointers. Int star time remaining equals int star. We're gonna cast this to an integer pointer. Malloc num processes times size of int. So we are gonna treat our burst times as remaining time, because we are not gonna run processes all at once. So we're gonna run them a little bit of a time, and then proceed to the next process after that. Run it a little bit of a time, and proceed to the next process after that. Run that a little bit of a time, and so on and so forth. We also need all of our other variables as before. So time elapsed, average waiting time, and average turnaround time. So I'll just steal that from SJF, but we need one more variable, and that is a bool to denote whether all of our processes have complete. So all processes complete equals false. And before we continue, because we are treating our burst times as time remaining, and we don't want to mess up our burst times that we passed in here, we're gonna copy them to a new array. So here we go. So I'm gonna say for int I equals 0, I is less than num processes I plus plus, and then I'm gonna say time remaining I equals burst times I. There we go. So now we've copied our burst times into this time remaining array here. So here's where it gets interesting. We need a while loop with 2 for loops as part of it. So while not all processes complete. We're going to repeat 2 different for loops in here. So let's begin with the second for loop because that's probably easier to understand. We are going to say the following. Check whether all processes have remaining times of 0. If so, then the program can break out of the while loop. So for that to work, give me a minute. Okay, as I said, we are going to iterate through every process's remaining time, and if if every process's remaining time is 0, then all processes are complete, and then we can break out of the loop. So I'll say all process is complete equals true. And then for int I equals 0, I is less than num processes I plus plus. We're gonna say this line of code. All processes complete equals, and the right hand side is a Boolean expression where we're gonna compare we're gonna say all processes complete and time remaining I equals 0. So what this does is it's gonna compare, it's gonna do a Boolean AND operation with all processes complete and time remaining I equals 0. So what happens is, if at any point we have a time remaining that isn't 0, the whole thing is going to evaluate to false. But it will only evaluate to true if every process had a remaining time of 0. And if that is the case, then all processes are complete, then we can break out of the for loop. So that was the second for loop. We need now the first for loop. So let me just add some more comments. Okay, so now we have the first for loop, or at least it's ready to go. So I'm just gonna begin with also say for each process with time remaining, if the process reaches 0 this way, calculate that process's waiting and turnaround time. So we're gonna begin that with a for loop as follows. For int I equals 0, I is less than num processes I plus plus. And then it's all a matter of filling in the blanks after that. However, there is one check we need to add in here, and that is if a process has no time remaining, skip it. So if time remaining I equals 0, continue. So that is our one check, and from there, it's just a matter of writing the rest of the code here. So we'll get to that in a little bit. Okay, so let's finish up that round robin function right now. So I'm just gonna copy this line here and paste it right before the while loop. So times for round robin quantum equals %I are as follows, and then I'm gonna add in comma quantum. So this is gonna be our I'm just gonna add a comment up here and say calculate each process's and waiting and turnaround time. Okay? Alright, so as mentioned, we need to iterate through our times remaining. We need to iterate through the array of remaining times, and for each time that isn't 0, if it is 0, you have to skip it. For each time that isn't 0, we're gonna decrement from that remaining time the quantum. If the remaining time is less than the quantum, then we have to decrement that remaining time instead. And that's because in round robin, if processes run in round robin for a fixed amount of time, so each process takes turns on the CPU. If a process finishes in less time, if a process were to finish before the quantum is up, then we just let in the next process after that. We don't have to wait for the quantum to expire to let in the next process. That's the thing about round robin. We run processes for that amount of time, but if a process finishes sooner than the quantum expires, then we just let in the next process. No need to keep processes waiting after all. Okay. So I'll just call this the current quantum. It's either the quantum or if the remaining time is less than that, it's the remaining time. It's either the quantum or the remaining time, whichever is less. So whichever is smaller, the actual quantum or the remaining time. As I said, if a process finishes early, we just let in the next process after that. So, int current quantum equals quantum if time remaining I is less than current quantum, then we'll say current quantum equals time remaining. So yeah, this was a fill in the blank in your instructions as well. So we need to calculate what the current quantum will be. It's either the quantum or the process's remaining time, whichever is smaller. Then we increment the elapsed time by the current quantum and decrement the current quantum by the time remaining. Decrement the current quantum from the time remaining. So I guess I kind of miswrote that. So so we're gonna increment the elapsed time, or was it time elapsed? Time elapsed. So I'll copy that. Increment time elapsed by current quantum and time remaining I minus equals current quantum. And then if a process's remaining time reaches 0 this way, calculate and print its waiting and turnaround time. So if time remaining I equals 0, we're gonna print out the remaining time. So no, we're gonna print out the waiting and turnaround time. So what I'm gonna do is the following. I am gonna once again go to one of my other functions here and just copy paste the code. So I'll just copy all that code and go back to this if statement and just paste the code. Because we have burst times already from our burst times here, so I can just... Okay, so there are a few things that we won't be using here. We won't be using this time elapsed line here because we already incremented it outside in here. So we just need the burst time, turnaround time, and waiting time. So turnaround time is time elapsed, which we had incremented already. Waiting time is turnaround time minus burst time. So now we should be able to print out, well, everything for that one process. So if time remaining is 0, we're just gonna print out that process's waiting time and turnaround time. And then we're gonna increment these two variables. That is our average waiting and turnaround time. So to calculate that, I'm gonna copy these lines of code and just add it to here, right after the for loop. No, after the while loop. Print out the average waiting and turnaround time, and after that we can say return 0. But before we return, we need to deallocate that memory. So we have a dynamically allocated array here. We need to free up that memory when we're done. So we're gonna say free time remaining. There we go. Okay, so let's just line up our code. Let's just give the code a good once over and see whether it works. So I'm gonna recompile the program once more. Okay. Oh, this is a void function, so it's just return. Nothing else after that. Try again. Okay, so with that compiled, oh, you know what I forgot? I forgot to uncomment out that function call. So let's uncomment that, and this is gonna run our processes for 3 milliseconds at a time. So let's try it out. I need to recompile it. So there we go. And now I'm gonna say ./project1. We are gonna run 5 processes with burst times of 3, 1, 4, 1, 5. Okay. Okay, it looks like I'm missing a parenthesis in my output here. So the times for round robin quantum 3 are as follows. Process 0 had a burst time of 3, so it ran for that entire quantum and finished running. Process 1 had a burst time of 1, so it also finished within that quantum, but earlier than the quantum would expire. Process 4 runs for 3 seconds, well, 3 milliseconds, but it stopped right way through because time was up. And then it goes to the next process after that, which is process 4. Okay, so the thing is this. The processes are printing out their waiting and turnaround times in the order that they completed. So process 0 finished first, and then process 1, and then process 3, and then process 2, and then process 4. So yeah, so the order is going to be 0, 1, 3, 2, 4, and that is the order in which process is finished. So process 0 finished first, then process 1, then process 2 had to run twice because it ran for 3 milliseconds the first time and then 1 the second time. In the meantime, process 3 here finished, and then process 4, no, and then process 2, and then process 4. So when you fill out your table, you gotta take note of which process was which. So especially with SJF, because we sorted the processes by burst time, so their times are gonna be all different. So yeah, and after that we can calculate our average waiting time and turnaround time, and now we have the necessary information needed to fill out our table here. or rather, we have enough information to verify that the results that we got in part 0, doing the whole thing by hand, were correct. And once we verify that's correct, we can get to work with the other bits of experimentation. So, I'm going to experiment with these 5 burst times, as before, and I'm going to change the quantum size from 1 to 2 to 3 to 4 to 5. So, 1, 2, 3, 4, 5. You know, I'm gonna add 6. So this is So this would be involved for your second part of experimentation, where you increase the size of a quantum to see what happens when you increase the quantum. So, I'm going to recompile the program here, and I'm going to use the same times as before. So, we're going to run with 5 processes with quantums, with the burst times of 3, 1, 4, 1, 5. So, with FCFS, we got a wait time of 4.8 and a turnaround time of 7.6. With SJF, they are much lower at 3.4 and 6.2. With a quantum of 1, it's 5.4 and 8.2. With a quantum of 2, it's 5.8 and 8.6. With a quantum of 3, it's 5.4 and 8.2. With a quantum of 4, it's 4.8 and 7.6. And with a quantum of 5, it's 4.8 and 7.6. And, oh, let me fix that. Okay, so, let's try that again. So, I am trying out these 5 processes with different quantum size for round robin. So, quantum of 1, 5.4 and 8.2. Quantum of 2, 5.8 and 8.6. Quantum of 3, 5.4 and 8.2. Quantum of 4, 4.8 and 7.6. Quantum of 5, 4.8 and 7.6. And then quantum 6 equals 4.8 and 7.6. And what does that look like? It's starting to look like first come, first serve. And that's because if we have a very large quantum, round robin, the point of round robin is to give processes a fair share at the CPU. Or I guess another way to put it is they all take turns on the CPU. So if we have a process, if we have, okay, so it's one process's turn, and then the next process, and the next process, and the next process. So they each have a turn at the CPU. If we have it so that, if it's such that each process has a very long time to run under round robin, if it's to the point where processes are just allowed to run from start to finish without interruption, this is how round robin becomes first come, first served. So, yeah. Anyway. And if we keep enlarging the quantum after that, then nothing's gonna change except for the fact that we just changed. Nothing's gonna change in terms of results. So, this is what happens when we make the quantum really large. In round robin, if we make the quantum so large that processes are allowed to just run non-stop from start to finish, then it starts to become more like first come, first served. Another thing that I would like for you to work out with these processes from part 0 is to figure out what quantum resulted in the best turnaround time and waiting time. So you want them to be as low as possible, but at the same time, shortest job first tells us what the best possible waiting and turnaround time will be. or rather the best possible average waiting and turnaround time will be. And we can't get any better than those times. So, as mentioned in our lecture, shortest job first, we cannot implement that in practice because we would need a means of figuring out how long processes will run for, which is information that typically cannot be determined ahead of time. So, for part 5, once we have done all of our programming, so it's part 5 that once we're done with all the programming, we can confirm the results from part 0, experiment with increasing the quantum, and then try it out with another set of processes. So I want you to generate a sequence of 6 random numbers, say from 2 to 10, to serve as burst times for a new set of processes. And then using those processes, find the average waiting and turnaround times for first come, first served, shortest job first, and round robin with 3 different sizes of quantum. So, really the hard part of this entire assignment here, of this entire project here, is just getting the calculators up and running. But once we have that, once all that is done, it's just a matter of punching in numbers and then seeing what times we get. Okay? So, that's going to be it for CSE-4600. I might have an extra video of what we're going to be talking about for Chapter 3. If I get around to doing that, it would probably be around Thursday or Friday that I'll have it out. If not, we'll be starting it on next Tuesday. So, we're going to begin our discussion on memory. If not this Thursday or Friday, then next Tuesday. And if I don't get around to posting a video, I'll at least have the lecture material on Canvas by then. Okay? All right. So, if you have any questions about the project, let me know. Ask away. I'm here to help. And with that, we can say that this program is complete. Pat yourself in the back, because if you've made it this far, then you basically have the entire thing done. The rest of the assignment from here is basically just punching in some numbers and getting results out of it. Okay? Alright. Okay. Alright, take care, and I'll see you next week. Alright.